Hello and welcome to this introductory clip to buffers, where we'll go through how buffers work, what it is, how we can make one, and how we can calculate its pH. There are some more applied buffer calculations that you need to be aware of, but they'll be covered separately in another clip. So buffers are found in lots of different biological systems, for example human blood, as well as many synthetic products. And they're described as a mixture of a weak acid and its conjugate base, and together they minimize any changes in pH. So I've annotated the diagram a little bit. If you add an alkali, the weak acid reacts with it in the form of OH-, obviously, to drive the equilibrium to the right. Whilst if you add acid, what happens is the conjugate base that's present in aqueous solution reacts with the incoming H+ ions. And as this happens, the position of equilibrium is shifted to the left. So in terms of Le Chatelier's principle, it can be seen quite easily what's going on. If you add an alkali, you're using up some of the H+, and it forms water. So the H+ that's lost needs to be restored. So therefore the HA dissociates and makes more of it. If you add acid, the H+ concentration increases, so the equilibrium has to shift to the left to try and use it up. So if you think about it in terms of first year Le Chatelier's principal ideas, it's quite straightforward to explain. So let's now have a look at how you might prepare a buffer based on a weak acid. So to prepare a weak acid buffer, you must have a reservoir of conjugate base, as well as some weak acid present. And it's also important to remember that the buffer will have a finite number of moles of each, so if either one happens to be used up by the addition of excess acid or alkali, the buffer will cease to work. And although the buffer might minimize pH changes, it won't prevent them entirely. So the assumptions that are made when we're talking about the model of a buffer based on a weak acid is that the conjugate base is completely dissociated and the amounts of acid or alkali added are small, so the buffer is not overwhelmed. So the first method for making a weak acid buffer is the most simple. You just add an excess of a solution of weak acid salt to a weak acid, so for example ethanoic acid plus an excess of sodium ethanoate. The second method is to add a strong alkali, such as sodium hydroxide for example, to an excess of weak acid, so some acid is left. But it's essential that the number of moles of weak acid is over and above the number of moles of NaOH. If it's not, all of the weak acid will be neutralized. And the third method is to add a small amount of metal to an excess of weak acid. Now metals and acid obviously react to make the salt of the metal. The salt of the metal is the conjugate base, isn't it? So here what we're looking at is making sure that the number of moles of weak acid is larger or greater than the number of moles of metal that you add. If it's not, again all the weak acid will be used up. So let's have a look at some examples here and see if you can work out if they're a buffer or not. So pause the clip and see if each of these mixtures are buffers or not. In the box at the top I put a reminder that a buffer must contain a weak acid plus its conjugate base. So the way to do this is to work out the moles of everything first and then see if the reminder in the box at the top of the screen is being obeyed. So pause the clip, give it a go and come back when you think you've worked it out. So for mixture A, working out the number of moles of methanoic acid gives us 6.25 times 10 to the minus 3. The number of moles of NaOH is 3 times 10 to the minus 3. So by difference, what's left over in terms of sodium ethanoate is 3.25 times 10 to the minus 3. So after the mixture has been constructed and put together, we have some weak acid and we have some conjugate base, so we have a buffer. So the type of buffer that we've got here is the second one, a strong alkali plus an excess of weak acid. Let's have a look at mixture B now. So doing the same type of calculation for mixture B, working out the moles separately of every species, you can see that you have more conjugate base than weak acid. So this is also a buffer. So these two examples, the moles of conjugate base has been an excess. It doesn't necessarily have to be an excess. It just has to be there. There has to be some conjugate base and some weak acid there for it to work. So these two examples happen to work as buffers. So this particular one that we're looking at here would be prepared by method 1 by adding an excess of a solution of weak acid salt, in this case potassium ethanoate, to the weak acid, ethanoic acid. So finally, let's have a look at mixture C. So in this case, what you do is you work out the number of moles of aluminium, you work out the number of moles of your propanoic acid, but we have a slight problem. Aluminium forms 3+ ions. The propanoate ion, as we've had a look at, is a single negative charge. So you would need 3 propanoates for every 1 aluminium. So therefore you need 3 times the number of moles of propanoic acid as aluminium to make enough aluminium propanoate. And we haven't got enough propanoic acid. So this mixture isn't a buffer because we don't have enough weak acid. So it just goes to show you need to check your moles quite carefully before you make the decision as to whether something's a buffer or not. Okay, at this point it would be quite good to try a few examples before going any further. So pause the clip for now, go and try some examples before we go on to how to calculate the pH of a buffer, because otherwise it'll be a little bit too much maths to take in all at once. So come back to the clip when you've had a go at some and started to get your head around this, and then we'll go through how to calculate buffer pH. So we're now going to look at how to calculate the pH of a buffer solution. Although it's loosely based on the Ka calculation you've done before with weak acids, so one main point you've got to remember is that the concentration of H plus and A minus are not the same, they're not equimolar. And this is because we have extra conjugate base, extra A minus, from elsewhere, either from the reaction of the weak acid with a metal, the reaction of some of the weak acid with a strong base, or by simply mixing it with some conjugate base in the way that we described a few minutes ago. So here's a typical exam-style question asking you to calculate the pH of a buffer. Notice what they're not doing is giving you the volume of either the weak acid or of the conjugate base. But it's okay because you don't need it. There's actually 2 methods of doing this, and both of which I'll take you through. It's really up to you to decide which you want to do. So either of these 2 methods are acceptable. The Henderson-Hasselbalch method is based on a specific relationship. So that expression I'm going to park there and come back to in a couple of minutes is called the Henderson-Hasselbalch relationship. So you can see it's based on pKa and some logs work as well, but you don't have to use that if you don't want to. I'm not trying to put you off it, but some people love it, some people hate it. I'm personally a bit ambiguous either way. It works, it's just as effective, but I'll come back to it in a second. Most people use the regular method based on Ka, which I'm going to focus on now. So the first thing to do is to write out the Ka expression. Now what you've got to remember is that H plus and CH3COO minus are not equimolar, so you can't simply turn the top part of the expression into H plus squared like you would do with a normal weak acid. There's another thing you've got to do instead. You need to make this the subject. So let's take both of those together. Now you can make the top part of the Ka expression the subject, the whole thing. So you move that over to the left of the equation to make it the subject. Now I need to isolate H+. So we get this expression instead, to which we can now put the numbers in. And that gives us a hydrogen ion concentration of 8.5 times 10 to the minus 6 moles per decimeter to the minus 3. So looking at the bottom left of the screen, that gives us a pH of 5.07, because I just plugged that number into minus log of H plus aqueous concentration. So now let's do the same calculation, but the Henderson-Hasselbalch way. So the first thing to do is to work out the pKa. So to do that, you do minus log Ka, which is minus log 1.7 times 10 to the minus 5, which gives you 4.77. So taking the other part of the equation, which is the log expression, it's essentially log 0.1 over 0.05, which gives you log 2, which gives you 0.3. So all you do is add those two together, which gives us exactly the same pH value as we used before. And like I said a couple of minutes ago, it doesn't really matter which one of these methods you use, because either of them are acceptable in exams. So it's really up to you to choose which one you're most comfortable with, and just stick with that. Okay, so I said I'd pause it at this point because more applied buffer type calculations are best done in another clip. We're almost up to 12 minutes now anyway, so there's quite a lot we've covered. So again, it's a really good idea now to go and try some examples of these to get yourself thoroughly immersed in this technique so you're comfortable with it and you're confident with it for when those exams come around. So in the meantime, thank you very much for listening, and until next time, see you soon.